Question 13 then, we have one of the, again, a classic kind of question where we're looking at what happens if we move something to another situation, another planet perhaps, another planet certainly in this case. What happens to the gravitational field strength maybe, or the weight, or these sort of questions come up again and again. So let's have a look at this one. Our first situation is very nondescript really. We have a planet, it's got a mass m, it's got a radius r, and it's got a weight w. And we're now working out what will happen when we have the mass being transferred. We're now going to put it onto a new planet. The planet is larger. It's got a mass 2m and it's got a radius 2r. Incidentally, this means that the density of this planet is going to be less. We'll come on to why that is in another question. So we're working out what the new weight is. We could call this W new, and we don't know what it is. All we know is we have to give this in terms of W, whether it's W by 4, W by 2, W, or 2W. So the first thing that we need to do is to flip this piece of paper because it is entirely the wrong place. There we go. Okay, so we have first of all our weight is W, our new weight, W new. We're going to need to work that out. That's the same as the force, isn't it? Because the weight of an object is just down to the force due to gravity, so we could call this F nu if we wanted to. The force due to gravity is going to be given by gm over r squared, or gmm over r squared rather. It'd be worth mentioning that W, the original weight, original force, is going to be gm m over r squared, Newton's equation there, of gravity. This new force, well, g is going to be unchanged, that's the universal gravitational constant, but the mass of the large object we're looking at now is now going to be 2m, isn't it? The mass of the object here, well, it's the same object, so it's going to be just little m again. And the radius here, well, that's going to be 2r. We need to square that, the whole thing. Remember, it's g times the mass divided by the radius squared. So the radius here is 2r, so it's going to be 2r all squared, and it turns out that becomes very important. So again, we're going to try and rearrange this in terms of what the original force was. W is gmm over r squared. So if we look at this, we're going to find that this is 2gmm over, well, this is 2 squared, so it's going to be 4r squared, isn't it? 2r all squared is 4r squared. So this is basically the same as gmm, dividing both sides by 2 r squared, which is the same as saying gmm over r squared divided by 2. So we're looking at basically the weight being divided by 2. So in other words, the answer is going to be B. The weight of the object is half what it used to be. And that is, of course, because we're moving away from the centre of the object. We're further away. Even though this new planet has a larger mass, it is much larger in size as well. It's twice as big, which means it has, in fact, 8 times the volume, and so on. So this is essentially W divided by 2, so the answer of that one is going to be B. Question 13 now, and we have again a similar situation, I suppose you could say. We have a planet, and they talk about the orbit of the planet in the start. Turns out that isn't relevant at all. Maybe put in just to throw you. We've got our planet, it's got a field strength on the surface of 8 newtons per kilogram, so just a little bit weaker than on Earth. And we're now considering this star. The star has a similar density, but the diameter is 100 times greater. So this is going to affect, of course, the distance from the surface to the centre. But this should be hopefully bring up warning signs inside your head, because you should also be thinking, well, if it's larger, it should have a larger mass as well. and we're going to need to work out how big that mass is going to be. So again, let's draw our two situations. First of all, we have our planet. It has a mass again of capital R and a radius of mass of capital M, a radius of capital R, and the value of G on the surface of the planet, we'll call it GP, is going to be 8 newtons per kilogram. Our new situation here, we obviously will not draw this to scale. We have a radius of 100 R here. We have a mass which we can call ms, the mass of the star. We don't know what it is yet, we need to work it out. Now, there are two ways that you can go about this. One is a kind of intuitive way. So you could look at this and you could say, well, if the radius is 100 times larger, you could be remembering that a sphere with 100 times greater radius is going to have a volume of 100 times 100 times 100 times what it was before. But we'll do it from scratch. We know that the mass of the planet is going to be given by the density of the planet times the volume of the planet. That's just the density, volume and mass equation. Similarly, we know that the mass of the star is going to be the density of the star times the volume of the star. You'll notice that I haven't bothered putting in planet and star subscripts here because we said that the density of each of them are fairly similar. So what we can work out from this, we're going to need to know the ratio of the volume of the planet to the volume of the star, because it will be the same as the ratio of the mass of the planet to the mass of the star, because they have the same factor multiplying in both cases. So we know the volume of the planet, Vp, well, that's going to be 4/3 pi r cubed. The volume of the star, let's draw a line separating them there, is going to be 4/3 pi, and then the radius cubed, well, the radius is 100 of course, so this is going to be r times 100 cubed. The radius is 100 times what it was before. So if we took this out here, we would know that this would be 4/3 pi r cubed times 100 times 100 times 100, which is of course a million. There we go. So the volume of the star is a million times the volume of the planet. So we know that the mass of the star must be a million times the mass of the planet. We can write this as the mass of the star equals 1 times 10 to the 6, short way of writing a million, times the mass of the planet. There we go. Our final part then is to work out what the surface potential of the planet is going to be, or GS. That is the question that we're trying to work out in the first place, this value here. So we know that the potential, or the gravitational field strength on the planet is going to be Gm over r squared. We know that on the surface of the star it's going to be G times the mass of the star. The mass of the star, we've said, is 1 times 10 to the 6 times the mass of the planet, which is here, Gm times 1 times 10 to the 6, which is just 10 to the 6, we can leave it like that, divided by the radius. We know the radius is going to be 100 r, and we're going to need to square that, of course. So we're going to try and rearrange this in terms of GP, in terms of Gm over r squared. So to pop this away, we're going to find that this is 100 times 100, so it's Gm times 10 to the 6 over r times 10 to the 4, which of course is just, or rather r squared times 10 to the 4, which is just Gm over r squared times 10 to the 2. Now of course we're noticing that it's Gm over r squared, it's exactly the same as Gp, so we've just worked out that the gravitational field strength on the surface of the star is going to be times 10 to the 2, which is 100 times greater than the gravitational field strength on the planet. Gravitational field strength on the planet is 8 newtons per kilogram, so our star's potential on the surface is going to be 100 times that much, so it's going to be 800 newtons per kilogram. So the answer to question 13 is going to be C. Quite a long one, that one.